So by the end of this lecture, you will be able to use thermodynamic tables to find properties and also identify the application and limitations of the ideal gas equation of state, and then apply the ideal gas equation of state in solving engineering problems. So if you want to read further about the contents that we are going to cover today, you can read chapter 2.6 to 2.8 of Fundamentals of Thermodynamics, the recommended text. Before moving into the contents of today's lecture, I want to emphasize one thing, or I want to rather explain one thing about the PVD surface. You remember we discussed about having different phases of substances in different materials, right? So you can see we have two PVD surfaces. We have two PVD surfaces in both sides. Like, let's call it this one A and this one B, right? So now we have two PVD surfaces. There's a difference, there's a slight difference in these two. If you look at the liquid solid region here, oops, so it's here, and the liquid solid region here is like this. We cannot see the surface because when we are changing to solid from liquid, it comes to the right, and in figure A, when we are moving from liquid to solids, it moves to the left. So basically the substance shown in figure A, the PVD surface for a substance that contracts on freezing. So when the substance moves to the left, that means as we freeze, then it contracts, right? So in the right, you have a PVD surface for substance that expands on freezing. So when we are moving from left to right, that means you move from left to right on the specific volume axis. So basically that means you are expanding, right? The specific volume is increasing, that means you are expanding. So now you can see there are two types of materials, and usually A is the general observation. So usually when we are moving from a liquid to a solid, it densifies further. But there are certain exceptions as shown in figure B, right? So in figure B, you can see that there's an expansion. An example for this kind of a material, for this one, it's going to be water. So did you ever think why ice is floating on the water? It's because of this thing. So when we move from liquid water to ice, then it expands. In other terms, the density reduces so that it floats on the water. Otherwise, we should not be able to see ice on the water, right? Okay, Deza, you can go on. Oh, sorry, both diagrams are labeled A. Okay, my bad. So let's clear that out. This is, let's call this B, and this is A. I didn't notice that it's A and B, right? So B is for a substance that expands when freezing, and A is for substance that contracts on freezing, right? So as I was explaining, the ice floats on water because it reduces density or it expands during freezing, and that difference of the PVD surface is reflected on the PV and TV diagrams. You can see that PV diagram here has this portion, and PV diagram for B has this portion. You can see that there's a difference in these two PV diagrams. So when you see this, like, then you know, if you see PV diagram A, then you know that it's for a substance that contracts on freezing. if you see PV diagram B, then you know that it's for a substance expands or freezing. But looking at the PT diagram, so this is very important. Looking at the PT diagram, we cannot see a difference. See here, both PT diagrams more or less the same, because the phase difference, like from liquid to solid, we cannot see a pressure temperature change, so we don't see where it is going inside. Okay, any questions about that one so far? Are we all good? Perfect. So let's move on. So in today's lecture, you will need the notion that we mentioned the last time. Compressed liquid tables are not always available for all materials, right? So this statement says those are not available for ammonia, CO2, R410A, and even for water, it is available for 500 kilopascals and higher. So this means we may not see compressed liquid tables for all substances that we are using, right? But still, we will have to do calculations on compressed liquids. So in such situations, we use saturated liquid specific volume at the given temperature, right? And to find the saturated liquid specific volume at the given temperature, you go to the saturated liquid tables, and then you look for the given temperature and you look for VF, right? So then comes the relationship that you see here. For a compressed liquid, the specific volume is the specific volume at or specific volume on the saturated liquid line at a given temperature. And you remember, the compressed liquid properties heavily depend on the temperature, not on pressure, right? So it's very important. The compressed liquid properties does not significantly depend on pressure. So in case if you don't have a saturated in case if you don't have a compressed liquid table, we always look for the saturated liquid table and get the properties on the saturated liquid line, VF, UF, HF, SF, the properties you have not learned as well. So, and find those properties for the given temperature, right? All right. So now you remember during the last lecture when we tried to find certain properties, like let's say for a temperature entry table, we went like 5 Celsius, we went like 5 Celsius, 10, 15, 20, it's the temperature, right? And then maybe we had VF values for each of these. But what if we wanted to find the VF values for an intermediate temperature that you don't see here? What if we wanted to find the specific volume at 7.5 Celsius? Then we don't have a table for that, right? So in such a situation, what we are going to do is we are going to interpolate between the two data points we have, and we assume during this or in this bracket or in this interval, the properties vary linearly with temperature or pressure, right? For an example, if you look at this graph here, you can see that you have 2 points. The red points are the points that we know, right? Let's assume that we want to find y value at this point in the middle, right? So let's say that x is 7.5 Celsius. This is something known. We want to know the specific volume at this temperature. Let's assume x is temperature in this context, and y is specific volume, let's say, right? So now you are interested in knowing the specific volume at 7.5 Celsius, or like, just to avoid any confusions, let's say 8.5. Okay. In order to do that, we assume the parameters vary against each other in a linear pattern. So doing that, we can say the slope of uh, the slope of this line segment is equal to the slope of this line segment, right? So by looking at the shorter line segment, we can write the slope of this line as y minus y naught divided by x minus x naught. And by looking at the longer portion of the line, we can write y1 minus y naught divided by x1 minus x naught. And if we configure this equation to find y, we can write y equals y naught plus y1 minus y naught, x minus x naught, and x over x1 minus x naught. So all these parameters are known, right? So in this case, we can find y. So this will be a common practice that you will be following in finding your properties from tables. It's not only for specific volume, it is not only combined with specific volume temperature, it could be specific volume and pressure, and it could be anything else, right? That you are about to learn in the coming sessions as well. Yes, Lisa, go ahead. So this is an assumption, Lisa, right? So we assume the interval that we have is so small, therefore the variation is linear. So in this course, all the brackets, all the intervals that we are considering to find the intermediate values will be assumed as linear intervals, or linear variation will be assumed to have linear variations. Did I answer your question? Perfect. So any questions about this one? Anybody who did not understand this idea? Because you definitely need that, or this concept, to answer the questions. Perfect. Okay, let's move on. Okay. All right. Now let's do a bunch of practice questions so that you can get a hold of the theories that we've been learning so far. So take 5 minutes and try to answer this question. And I know that most of you are in front of your computers and you don't feel like grabbing a paper or like pulling out the notepad in your computer, but please do that and solve this by yourselves right now. So that way, I'm not going to see whether you solved it or not, but that way you save time, right? So anyway, you are staying with me for this coming 2 hours. So why don't you make the most of it? So take 5 minutes. I believe like you familiarized yourself with the question already. So given the time limitations we have, like let's try to move on to the solution now. The first question is, what is the point that holds the lowest pressure for liquid CO2? Anybody got the answer already? So this is the liquid portion. Perfect. So it's correct. Scott and Stephen got it right. And triple point, like this is the liquid region. So there, the lowest point that we can have a liquid is at the triple point, right? So then What is the phase of CO2 at 1 megapascal and minus 10 Celsius? Anybody who got the answer? Perfect. So Alexandra got it right. Wenli, awesome. So now, what is 1 megapascal? So it's going to be 1000 kilopascals, right? So this brings up a very important discussion. Always look into your units and don't let the units misguide you. So if we have 1 megapascal and check what we have in the y-axis, it's kilopascals. So we take 1000 kilopascals here, and then along that we go across the borders, and then the temperature again, it's given in Celsius, but in the figure it has Kelvin, right? So in exam situations, if you panic too much and if you have not practiced too much, then this could be an easy trap. So you might look into this figure and say, okay, I don't have minus 10. How am I supposed to locate these points, right? So, but if you see this is Kelvin, then you will not be confused. So minus 10 is 263 kelvins, right? Minus 10 Celsius is 263. So basically the red line down here, we can go up there, and then we find this point, which is in vapor region. Your friends got it perfectly right. Okay. And then the third question, CO2 at 15 Celsius. What's that again? So like exactly, Wenli is right. So kilo, mega, giga, tera, like it goes like every unit is multiplied by 10 to the power 3 if it is kilo. Like if we have 1000 kilos, that is it here. If we have 1 kilo, that is 1000 grams, and if we have 1 mega, that is again 10 to the power 3 higher. Okay, perfect. Robert, kilo is 10 to the power 3 of grams, right? So 1000 grams equal to 1 kilo, and then 10 to the power 6 grams, right? It's equal to 1 mega gram if we have it, 1 megapascal, right? Oh, perfect, perfect. Sorry, my bad. Thank you for supporting. Okay, now I think we made one mistake here while solving the problem. The temperature. So temperature is supposed to be 263 for minus 10, like it should be starting from here. And this is the point that we are interested in. Any questions about question number 2? Or are we all clear? Anybody still having confusions? Perfect. Now let's look into question number 3. It asks CO2 at 15 Celsius. So 15 Celsius in Kelvin scale is going to be 15 plus 273.15, right? It is essentially around 288. So close to 90, but 288. So we locate that temperature here. And then the pressure is 1 atm. So 1 atm is 1 atm is equal to 101,325 pascals. Okay, so it's roughly 100 kilopascals, right? If we divide this by 1000, it's roughly 100. So we locate this pressure now, and then we go and see the interaction. Okay, now we are here. So if it is cooled, so cooling means we are reducing the temperature, right? So cooling essentially means we are reducing the temperature, therefore we are moving in this direction. So it asks if we keep cooling, at what temperature will it start to change phase, right? So now we go until we have an interaction with one of these lines, and then after crossing this line, it will change from vapor to solid, right? So if we come down here, this is the temperature that we are interested in, right? It is roughly 195 Kelvin or 194 Kelvin, right? So when the phase is changed, would it be liquid or solid? So it will be solid because we are crossing the fusion line, right? Any confusion? We are crossing the sublimation line. Yeah. Any confusions or any questions? Perfect. And now we look at question number 4. CO2 at 1 atm is compressed at a constant temperature, 15 Celsius, right? So we already located this point. We already located CO2 15 Celsius and 1 atm. This is the point that we are interested in. So we started here, and it says we compress at a constant temperature, right? So the temperature does not change, and we keep on compressing. So like we have to go up on this line, right? So will it enter the liquid phase or solid phase first? So we cross this line, saturated liquid vapor line, and then we enter the liquid phase, right? So draw the process. So now to draw a process, what are the important steps? What are the important steps? There should be a starting point. There should be an end point. Sorry. There should be an end point, and then we should indicate the direction, right? 4.1 to 4.2, like these are the names for the points. You can use A, B, C, whatever the name you like. Any questions about that one? Are we clear? Perfect. So take about 3 minutes for this question and try to solve it yourselves. Okay. So from last lecture, you remember that the saturated liquid vapor region is represented by the portion that is shown in red color, right? So if we want to mark the saturated pressure for a given temperature, then you have to mark it like this, right? On the line, right? And it's here. And now let's go with the pressure first. So if pressure is higher than Psat, that is somewhere here, right? Let's call this P1. And if pressure is equal to Psat, this is going to be on the line, that is P2, let's say. And then if pressure is lower than the saturation pressure, we can call it P3. So it asks us to show if P is greater than Psat, the fluid is in compressed liquid region, right? So then this initial point was picked as the saturation pressure, and if our pressure 1 is higher than saturation pressure, that means it's in the liquid region. P1 is in the liquid region, the point 1, right? And that means it's a compressed liquid. If the pressure is on the saturated liquid vapor line, then it's going to be a saturated liquid, two-phase mixture, right? So you remember last time when we were discussing, when a point is on this line, we call it a two-phase mixture. Maybe it could go to saturated liquid line, or it could go into saturated vapor line, but not beyond that, right? So if the pressure is lower than the saturation pressure, then it's going to be in the vapor region as shown here. Any questions so far? Are we getting clear? Perfect. So you can try yourselves later how to interpret the same thing with temperature, with respect to temperature. Okay. So let's move on to the next one. So try to solve this question. Take about 5 minutes. So there's a question, when doing the last question with respect to temperature, is that with a PET graph as well, or is that meant for TV graph? No, even with the temperature, like you can use the same PET diagram as we had here before. So you simply mark the temperatures instead of pressures, like so. We can mark saturated temperature T2, and then we can go both ways. It says in question 1, when T1 is less than T2, what happens? T1 here and T2 here. So now you can comment on the points T3, sorry, T3 here. Now you can comment on these points as we did earlier. Did I answer your question? So there's another question. So temperature, saturation temperature of different saturation pressures are different. Yes, if that's what you were asking, it changes. Yes, Ryan.
So I was just looking back at the compressed liquid slide that shows our pressure and temperature graph as well. I noticed that they have different shapes to them. Looking at our critical and triple lines. So I'm curious on when we know which one to use.
Like for a given substance, if we ask questions like what we have there, so you should be provided with the graph applicable to that substance, right? So if you look at the left hand side, it is kind of similar to what we have, other than the curved shapes of the lines. It has a basic idea of what we discussed right now. And if you have something similar to right hand side, it's slightly different. But in either case, you should be provided with the TV diagram to comment on these things. Did I answer your question right?
Yeah. Okay. So for the question we're working on right now, we're just using the same graph we've used for the last few questions, just because it doesn't specify which like element or substance is used. Like
for TP, like for TP and PV graphs, right? Like it is not going to be different, because you have, like, if you look at this one with the contracting and expanding substances, the bottom half changes, right? So, but the question that we are discussing right now has nothing to do with the bottom part. It only deals with the top half of the dome. So throughout the course, this part will be the one that we are dealing most commonly, and we'll not be doing any calculations on the bottom part. So the difference of contracting and expanding substances will not impact our calculations using the two-phase region, saturated vapor, and compressed liquid.
Okay, thank you.
Okay, so to make your life easy, I will draw the dome shape for a TV diagram, and the same shape we will draw for PV diagram. And throughout the lecture series, these two dome shapes will, the difference of the shapes does not really matter for us. We just indicate these lines to indicate what's happening and what regions are there in the graph. So we'll be dealing with this dome shape only. We'll not have to deal with the contraction or expansion of the solids. Thomas, isn't water the only one that expands when freezing? So I know that water expands when freezing, but I don't know whether it's the only one. So that is something we'll have to check if we are interested in. So on TV diagram, if we start with TV diagram, this problem only asks for one explanation, either TV diagram or PV diagram. But for clarity, let's try to interpret both, right? So mark T equals T set and T equals T set line on this TV diagram, okay? So this is going to be T equals T set, right? This is going to be T equals T set line. And now, you know that inside the dome, pressure and temperature does not change. Let's say for a given T saturation, we know that there's a given P saturation. So now inside the dome, both of them will be constant, right? So similarly, if we wanted to mark P equals P saturated line on PV diagram, we can do that as well. P set. And then indicate the given state on it. The question says T or saturation temperature or X are given. T or X are given, right? Temperature or the temperature and the quality are given. So if the temperature and quality are given, we can easily locate this one. When we see the name quality, what can we say about the phase of this one? Phase of this substance. Is it a compressed liquid, or is it liquid vapor mixture, or it's superheated vapor? Any idea? Two phase, right? Perfect. So all of you got it right. So Mena has a question why we did not draw the same graph with the triple line on this question. So the question itself asks for TV or PV diagrams. That's one reason. And the other thing, like for the calculation purposes throughout this course, we will not be dealing with PT diagrams. Like it's just to identify the phases. That's what we use it mostly during this course. And TV and PV diagrams are the ones that we use for our calculation purposes. Perfect. So now when we know that it's two phase, we know that it's inside the dome, like, right? So somewhere here we can mark the same thing, somewhere there. Anybody have confusions how we pick the point? I believe we are all good. And then it asks us to label VF, VG, and write V in terms of VF, VG, and X. VF, VG, and similarly on PV diagram, it's going to be VF, VG. And our substance of our state, the specific volume at our state that we are interested in, we can call it specific volume as V. Any questions so far? Anything that's not clear? Okay. So now, in addition to this, like we'll do the derivation in the coming slides. So in addition to what we learned already, like you need to be able to draw these lines. If we want to draw a constant pressure line, right? Let's say inside the dome, we know that the pressure and saturation, pressure and temperature are going to be constant. So the pressure temperature relationship for a given pressure is going to be parallel to the specific volume axis, right? But outside the dome, what happens, right? So when the temperature changes, specific volume change. Therefore, it's going to be like this, and this is a constant temperature line, P constant. Okay, and if we want to draw a constant pressure line, a constant temperature line on the PV diagram, it's going to be like this. You remember, in subcooled region, even if the build up, the specific volume change is negligible, right? That's why we have this portion of the line as almost a vertical line. So anybody have any issues with what we have discussed so far, like drawing constant pressure lines or isothermal lines, constant temperature line? Any issues? Are we getting it perfectly clear? Perfect. Now, you remember how we derived the expression for quality in the last lecture. So this derivation is the same idea. So I'm not going to redo the expression or like redo the derivation. So you can look into this solution, or if you are not still not clear, then you can go back to the previous lecture video and then you can track down the applicable slide and get the idea. Okay, so now we jump into the most important discussion today. All the previous questions were like theory discussions and a revision of theory of what we have done, but this one is about reading tables. How do we get the properties from the so-called thermodynamic tables, right? And I know that you are not well aware about how to do that yet. Therefore, I'll do the first example with you. Okay. So in the first example, the pressure is given and the phase is mentioned, saturated vapor. So when we know it's a saturated vapor, then let's say when we draw our dome like this, where should we mark this point? One, two, three, 4. So should we mark this on point 1, 2, 3, or 4? Any idea? Oh, maybe I have given you a wrong impression, because saturated vapor, right? It's not superheated vapor. So when, yes, now you guys are getting it, because this point, this portion of the line is specifically told that saturated vapor line, right? And this portion of the dome is told saturated liquid line. So when we hear the word saturated vapor or saturated water, right? Saturated water, it's going to be this one. Saturated liquid should be more accurate, but we can, if we see saturated water, then again saturated liquid line, right? And if we see liquid plus vapor region or two-phase region, then where should we mark the point. 2. Perfect. And if we see superheated vapor, then where should we mark the point? Perfect. So if we see compressed liquid, where should we mark the point? It should be 5, right? I just added it because like we did not have a point in the compressed liquid region, because it should be outside the dome, again to the left, right? So if we wanted to mark the critical point, so it should be top here above the dome, on the dome, like at the top where the saturated liquid and saturated vapor line meets each other, right? So now as we are clear about this portion, now let's jump into the question solution. Okay, so assume all these questions, like I mean all these properties have to be found based on water, right? And if it is water, what we have to do is we have to find water tables first. This is very important. Step 1, choose water table, because in an exam rush, you will jump into methane tables and look into the temperature and grab some values and put that in your calculations, and your calculations will be wrong, right? So in the question, I should have mentioned it's water. Like that's why I said we'll assume that it's water for this question. Can a dome diagram exist if there are only 2 phases that occur? Alexandra, your question is not very clear to me. So this dome is the projection that we got from the PVT, right? So like here in both cases, right? So the dome does not change depending on whether it's expanding or contracting as well. So it's the projection of what we have here. Did I answer your question? Perfect. So now once we find, I want you, all of you, to go to Canvas, and under important documents you will see a document called all tables combined. Please download that immediately, right now. Let me know once you have downloaded it. This is the table that I'm referring to. It says all tables combined on top as the title or file name. Let me know once you have downloaded and opened it. Okay, so all of you downloaded it. Now I want all of you to go to that table and press Control F and type water. And when you type water, you can keep on pressing enter, and then you will go across different thermodynamic property tables, right? And then you will come across saturated water tables, right? In saturated water tables, for this question, what should we pick? Pressure entry or temperature entry? Pressure entry or temperature entry? Any ideas? We should pick pressure entry because we have been provided with pressure and we have a nice round number, and it's always easy to find that using the pressure entry table. For those of you who don't remember pressure entry and temperature entry tables, it's just are there for your ease of use, right? In the pressure entry tables, we have nice round pressure values as the first column. In temperature entry tables, we have nice round temperature values as the first column. So if you solve any question using either of these, it's not going to be wrong, but one table might help you save time, right? In this case, If you go into saturated water pressure entry table, you can find 400 kilopascals. Have you located this point? Tell me once you have located this one. Perfect. So once you locate this line, you see that right along the pressure column, right beside the pressure column, you have a temperature column, right? Then from that, you can grab the temperature applicable for this particular case. So if you go to pressure entry tables and scroll up or down, then it should have it. Found it? Perfect. And now this temperature number or temperature value can straight away go into our answer, right? It asks for temperature. Now, specific volume. What should we pick for specific volume? We have three values, VF, VFG, and VG. What should we pick for this current case? It should be VG, right? Because we are on the saturated vapor line, and Vg represents the value of specific volume on the saturated vapor line. So now we pick the Vg value and then we put it here. And how about the quality? Quality cannot be found from the table. So how do we note the quality? Any idea? Quality is X, right? X equals M vapor divided by M total. So what can you say about X? Any guesses? Any ideas? On saturated vapor line, if our state is on saturated vapor line, can we have liquids there in our mixture? If we are on the saturated vapor line, can we have liquids on there in our mixture? No, right? Because saturated vapor line stands for this. We have the liquid vapor region, and if we keep providing energy, then all the liquid in the substance will join the vapor phase, and then once it has joined that vapor phase altogether, we call it saturated vapor line at that point, right? The boundary condition. So there we don't have any liquid, therefore the X is going to be 1. So all of your answers are correct. Okay, so in this case it's important to note, okay, let's assume that our data point was in the superheated region, as I'm just marked by the X, right? And if it is in the superheated region, like, what do we say about quality? Do we go like 2, 3, 4, 5 like that, or we just say non-applicable? Awesome. It is non-applicable, right? For superheated or compressed liquid regions, the quality is non-applicable. It's not relevant. So we are not going to deal with that. So in this case, it's going to be 1, right? If it was on compressed liquid region, no. If it was on saturated liquid line, then what is the quality of the mixture? It's going to be 0. Perfect. Perfect. You guys are nailing it. So now, for every question we do, I suggest you to do this all the time. So every question we do, please, in PV diagrams, please mark isothermal lines. In TV diagrams, mark constant pressure lines or isobaric lines, and try to point or try to locate your data point, right? So try to locate like this point. Like in this case, it's going to be on saturated vapor line, and again here as well the same idea. And on TP diagram, it's going to be on this line. In two-phase, how to find X? So how to find X is dependent on if the data given, you have to either be provided with specific volume or quality, right? So when you have enthalpy, entropy, and internal energy parameters like that, you can find them to use quality as well. But with the current knowledge we have, if you were asked to find quality or specific volume inside the two-phase region, you should be given either of these parameters, either quality or specific volume. Really, did I answer your question? Perfect. So now I will solve this one as well. No, I will not solve this one. So I will give you 3 minutes to solve the part 2. Yeah, sure. So if we have our state on saturated vapor line or saturated liquid line, then it will be 1 or 0, right? So if our substance is located on saturated vapor line, that means all the substance is in vapor condition. So vapor mass divided by the total mass, it's going to be 1, right? Are we clear on that one? Perfect. So if it is on saturated liquid line, then what can you say about vapor mass over total mass? On saturated liquid line, we don't have any vapor. So basically, vapor mass is 0. So vapor mass over total mass is going to be 0. Okay. And if it is inside the dome, then there's vapor and liquid in equilibrium. So depending on the conditions, so the vapor mass has to be added. If you want to calculate the X after knowing the specific volume inside the dome, you can use this equation, right? So this one was used to calculate specific volume once the quality is known. If you reconfigure the same equation to calculate X, then you can do. To calculate the specific volume or quality inside the dome, you should either know specific volume or X. You cannot know, I mean, if you don't know both of these, with the current knowledge, we cannot find quality. But once we get to know internal energy, enthalpy, entropy, and all these other parameters, then there are ways we can calculate the quality based on those. But for now, we have to know either of these parameters to calculate the remaining parameter. And if we are outside the dome, like somewhere here or here, then there's no quality. Quality is only for the dome, the saturated liquid line and saturated vapor line, and the region inside the dome. So this portion only, this portion and the boundary lines. Okay. Perfect. So Wenli, what table did you use to answer this question? Pressure entry or temperature entry? Page 9. And what is it, a temperature entry table or pressure entry table? So what is the first column? Is it temperature or pressure? Perfect, right? So by just looking at this one, we can assume that we have to use temperature entry because it's convenient, right? It has a round, nice round temperature figure. So we have to use temperature entry. And it says saturated water. I would prefer to put saturated liquid water or saturated liquid. That would have been much clearer, but saturated water is fine. And now, just by looking at these numbers, can we say the value of X already without looking at the tables even? It's going to be 0, right? Because it's on the saturated liquid line, so it's going to be 0. So now we are just left to find pressure and specific volume, right? If we go to our temperature entry table, you can now locate 20 Celsius as seen here. So once we locate the 20 Celsius, then right alongside it, we have the pressure. So this is going to be our answer for the pressure, right? And after getting the pressure, now we need to find the specific volume. What should we pick? VF, VFG, or VG? Perfect. All of you are correct. Now we are getting it perfectly right. So now we pick VF and we put that here, right? So again, importantly, try to locate. Give me 1 second, Christopher. I'll answer that again. So try to locate your point on PV, TV, and PT diagrams, right? While you are solving the problem with us in the class. So all of you, please try to locate these points. If you have any difficulties in locating these points, please let me know as we go along with the question solutions, right? Okay, now why VF? Because it says saturated water. So I already mentioned that it should be saturated liquid for better understanding. So if it is saturated liquid, then VF is going to be this guy, right? So VF is this, the specific volume on the saturated liquid line. So basically, in this case, that's what we are looking for. Did I answer you, Christopher? Perfect. Can you explain again why for the previous one x was equal, x was 1, and for this one x is 0? Yes, of course. So x is mass vapor fraction compared to the total mass, right? In the previous one, it was totally vapor because it's on saturated vapor line. When it is on saturated vapor line, we only have vapor, right? So there, the total mass and vapor mass equal to each other. So the same parameter or same value divided by the same number, like 2 divided by 2 or 1 divided by 1, it's going to be again 1, right? So if it is on the saturated liquid line, so we don't have any vapor left because it's totally liquid. All the substance is in liquid form. So that means the vapor mass is 0. 0 divided by some value, that's going to be 0 always. Did I answer your question, George? Perfect. So now, this problem is kind of tricky. Like, so I'll solve it myself with you because you have not been exposed to something like this earlier, right? So the pressure and specific volume is given, okay, but temperature or quality or the phase is not given. Now we have to play with what we have, okay? So as the out of 2 temperature and pressure parameters, we only have the pressure. So as you all can assume, I will start the process with pressure entry tables, and we don't know whether it's saturated or not, but we start with saturated water pressure entry tables. Okay, so we'll start with saturated tables, and if we find out that it's not in saturated region, we can look into the other tables. So for now, I look for the saturated water pressure entry tables as I have pressure in my hand, right? And I try to locate my pressure point. Okay, so 10,000 kilopascals. I located my pressure. Now we don't know whether this is some saturated table, right? Saturated region. or two-phase region. So we have to find out that. Now, in addition to pressure, the only parameter that I've got is the specific volume. So now I try to compare my specific volume with what I have in the table, right? My specific volume is 0.003, right? Which is obviously greater than VF value here under the pressure that's given. VF value is 0.001, right? And it is lesser than the VG value for that given pressure, right? 0.003 is lesser than 0.018, right? So that means my specific volume is somewhere between VF and VG for that given pressure. So by looking at that, I can conclude that it is in the liquid plus vapor region or two-phase region. Okay. Anybody having issues right now? Like, or everybody got it perfectly clear? Are we getting it clear? Perfect. Deza got it. So anybody who's having any confusions? Yes, Christopher, you are getting it perfectly right. So for a given pressure, let's say in this case, 10,000 kilopascals, we check our VF and VG values at that pressure or temperature, either, like whatever the given parameter, and then if our specific volume is in between our VF VG values, then it is inside the dome. Basically, what this says is, let's say this point is VF, right? And this point is VG, and our point is somewhere here. Our specific volume is somewhere here. Are we making sense here? Perfect. Now we have nailed down that it is in this condition. So we can say this is the temperature of the substance, or this is the temperature of this state, right? Because we know that it's in two-phase region, and for the two-phase region, pressure and temperature comes as a pair. So now we had pressure already given to us, so we located temperature now, and then specific volume is given, so we don't have to calculate that. And to calculate X, or the quality, we gave away this equation in the last lecture. So then we can just plug in our numbers. The specific volume of our substance is given by V, so we put that one, and VF and VFG can be taken out from the table, right? And then we calculate this X value and we plug that in this table. And what's the phase? You can say L plus V, that means liquid plus vapor region, or you can say two-phase region. Okay, so in any case, we cannot, I had a question whether we can find X from the table. We cannot find X from the table. The quality cannot be found from the table, but the data from the table can be used to calculate quality. Are we clear? Perfect. And this one, so I will let you play with the third one. So try to find what's going on with the, not the third one we already did, fourth one. Take 2 minutes and try to find what's going on in there. Like we don't compare VF against Vg, like we compare our specific volume, the V value, against Vf and Vg to see where it falls. Did I answer your question? That is one way of doing it. Like if you go to the last slide of the lecture we did yesterday, it has all the conditions that we can use to check whether a given substance in saturated conditions or in the compressed or superheated liquid regions, superheated vapor regions, sorry. Right? So this is one way of doing it. So when we have temperature and pressure both, you can use either of these tables, right? You can start with pressure entry or temperature entry. It doesn't really matter. If you can find your pressure value in pressure entry table, then you can start with that one. If you want to find your temperature value with your temperature entry, then you can start with that one. So in any case, if you don't see your temperature or pressure in that table, that gives you a hint about something, right? So if you start with temperature entry and if you fail to find 190, so that may give away a hint for you. If it is there, then you can process from there. Okay, let's start solving this together, right? So in this case, I have picked pressure entry table. So out of the two, like I just picked pressure entry, right? We can use both. Now, my pressure is 1000 kilopascals. That's the easiest part. So I like this part very much. So I can just locate. Now, the temperature, here comes the confusing part. The temperature we have here is not what we have in the table. The saturation temperature we have here is lower than the temperature we have for the given substance, right? At this point, we need our knowledge about PV and TV diagrams to locate our data point and see what's happening, right? So if we start with PV diagram, so let's see, in PV diagram, let's draw an isothermal line, right? In this isothermal line, if our this diagram can be used, sorry, we can start with PV diagram if we started with temperature entry. I'll tell you why in a bit, right? Let's start our discussion with TV diagram, right? There we draw constant pressure lines for 1000 kilopascal, right? For 1000 kilopascal, this is our constant pressure line. And now, do we know the temperature here? The temperature reading, this one? Anybody? Do we know the temperature at this point, at this level? Not 190, no. 179.91. Excellent. So the idea is we are looking at 1000 kilopascals constant pressure line, right? In the saturated region or two-phase region, no matter what, whatever we have in the question, it doesn't matter, right? So it's a state. In the saturated region, we should have the saturated temperature and saturated pressure. So for a fact, we know that this reading is going to be 179.91. Right? Are we clear on that regard? I assume you are. And if you have any questions, please feel free to put that in. And now our temperature reading is 190. Right? So our temperature reading is 190. Now what we can do is we can try to draw a line at 190. This is 190. Right? So you can see the 1000 kilopascal line is only intersected at 190, and it's not intersecting our pressure inside the dome, but in the superheated vapor region. By looking at this observation, we can say that this is going to be in superheated vapor region. Are we clear? Any confusion about that? Perfect. Now, if we look at PT diagram, right? Let's say for our given pressure, this is going to be the saturation temperature. So let's say this is 1000 kilopascals, and what is the reading in the temperature scale is going to be here. Anybody? For 1000 kilopascal, like we draw 1000 kilopascal line here, and now we want to know the temperature reading at that point. What is it going to be? It is going to be 179.91 because it's on the saturation line, right? So it is going to be 179.91. So our temperature given is 190. So it should be somewhere here. So again, we confirm that it's in superheated vapor region, right? Don't misinterpret the data we have been provided with the question. It is not the ones that determine like what are the pressures and temperatures on the table. Like we have to compare our values with the table just to confirm whether our state is inside superheated vapor or liquid plus vapor or in compressed liquid region. So are we clear on that one? What we did in PT? Okay. So now let's start identifying the same with PV diagram, right? So in PV diagram, we mark our temperature. In previous cases, we started with, in TV diagram, we started with the pressure, and in PV diagram, we start with our temperature. Okay. So this is T constant, and the temperature value is 190, right? The temperature value is 190. And now the pressure, the saturation pressure at this point is going to be what? So we have to go into our temperature entry tables. If you started with temperature entry tables, then you have to go into your temperature entry tables and find what is the saturation pressure. Can somebody do that? What is the saturation pressure for 190? Okay, perfect. 1254. Sorry, this is too small of a space to write. So I write the pressure reading at this point, 1254 pascals or kilopascals, yeah, right? And our pressure reading is 1000. So 1000 is going to be somewhere below this pressure. So if we draw 1000 kilopascal line, so it is below this saturation pressure. So it intersects our isothermal line outside the dome in the superheated vapor region. So again, we can confirm that this is in superheated vapor region, right? Are we clear on that one? I assume we are. If you are not clear, like then down in the road, like we can discuss as you put up the questions. Okay. So now in three ways, in using three diagrams, we figured out our phase is, for this given question, our phase is going to be superheated, right? Superheated vapor. Now we have that. And what about X? X is non-applicable. You remember, we agreed that the X is only defined for saturated liquids or saturated vapors or substance with liquid vapor equilibrium, right? So basically, anything inside the dome or on the boundary lines have X defined for them. But superheated vapor or compressed liquid doesn't have anything to do with X. So it's non-applicable. Now we need to find a specific volume for this superheated vapor. So we have to jump into superheated vapor tables in order to find this one, right? So I want all of you to go into your table set and find superheated vapor tables for water. And try to locate your condition. So you can see these are your superheated vapor tables, right? So in superheated vapor tables, unlikely to the saturated water tables, we have a different setup. We have a temperature column. Oops, I cannot highlight the column here, but we have a temperature column, and at the same time, on top of each block of table, like we have a pressure value. So our first goal is to find the applicable pressure reading for our case, which I remember to be 1000 kilopascal, right? So we go on searching for 1000 kilopascal. We go down, and further down, and then we find 1000 kilopascal, right? And then we need to locate our temperature, 190, right? So in this table, saturation conditions are given in the first line, right? So it is 179.91 Celsius, the conditions for 179, right? And also we have the values for 200, the property values for 200 Celsius, but we don't have the values for 190. Therefore, we have to do interpolation. You remember, I mentioned if we don't have the exact value, then we take that interval of data we have and then we interpolate, assuming a linear variation within the range, right? So if I go back to the slide, now you see that the saturation temperature value, that is going to be 179.91 Celsius, right? So we have two boundary conditions for temperature, 179.91 and 200. And what we are interested in is the conditions of the substance at 190. So we know that as well. What we want, we already know, right? So we need to find the specific volume at 190. Now, from the table, we can get the specific volume at 179 or the in the saturated conditions. So that is going to be 0.19444, right? And then again for 200 Celsius, we can do the same. We find this one, the specific volume. For now, don't worry about the internal energy and enthalpy and this section. Forget about this for now. We don't need this portion yet. After doing that, we just substitute the numbers into our interpolation equation, right? So you remember for a linear interpolation, we derived this equation earlier. So y is the parameter that we are interested in, right? So you can substitute all y's with specific volume because we want to find specific volume, right? So v is the specific volume at 190. V0 and V1 is going to be the conditions that is going to be replacing Y0 and Y1. And Temperature values are what we have at this point, the known parameter. So we replace all x's with t. And once you do that, you get the specific volume for the superheated vapor at 190 Celsius. Please try to solve this one together with the class. Like take 2-3 minutes and see if you have any questions. This is very important. In this part, you learned how to use superheated tables and at the same time how to do interpolation for unknown values to determine the unknown values or the values not provided in the table. Okay, anybody who solved the question and like got it perfectly right, I mean with me or without me, it's fine, but let me know once you have completed the full answer. So I think all of you have got it. So if you have any questions, please feel free to ask, because in these steps, it's very important that you understand it properly, because in the coming lectures, I will not be spending too much time on explaining how to interpolate. Then I will say, okay, we did interpolation and move on, right? So that's why I'm emphasizing these ones. If you miss the tiny bits down in the road, then it will pile up and it will make your life difficult when you are trying to solve more complex questions. Okay. So again, now we can find, like, you can work on this one from the knowledge you have in the previous question. So you can work on this one, the last one. Take 5 minutes and give me the answers. Perfect. So Wenli found that it's compressed liquid. Okay, let's go on. So Wenli, what table did you use? Like, is it pressure entry or temperature entry to start with? Okay. So now here we are. So we can use pressure entry or temperature entry tables to find this matter. So I have picked temperature entry here. So you can determine the state using either of these, right? So let's start with the temperature entry as I have it here. So now for 10 Celsius, the first step, easiest and the most delightful step, locate your condition, 10 Celsius. And now at 10 Celsius, your pressure is what? Your pressure is 1.22, right? So like the saturation pressure is 1.22, but you have a higher pressure, right? So what you do is you go to a PV diagram and then you locate or you draw an isothermal line as shown below. So you draw an isothermal line, right? And there at this point, the pressure is known. The pressure is 1.22. 1.22, right? So if it is 1.22, our pressure is given to be 10 kilopascals. 10 kilopascals. So what can we say about the state of this one? So our state only crosses the isothermal line in the compressed liquid region. Therefore, we can say that this is a compressed liquid, right? Are we clear? Perfect. So now you can do the same with TV diagram. So we did it earlier for determining whether something is superheated vapor in the previous example. So I'm not going to solve it using other two diagrams, but I highly encourage you to do it at home and see whether you can come to the same conclusion using TV and PT diagrams as well. Okay, so now once we know it is in compressed liquid region, so we can say that we can remember that we said if it is in compressed liquid region, out of the temperature and pressure, what determines the properties of a compressed liquid more? Is it temperature or pressure? What has a more significant impact on properties of a compressed liquid? Any ideas? In the first slide or second slide of today's lecture, we had this idea. So is it temperature or pressure has created more impact on compressed liquid? It's temperature. You remember the example. If at any point, if you are not sure what is the parameter, remember the example I told you. Like, think of a pop bottle filled with water and you try to press it hard, but the shape change and the volume change that you see is negligible. But if you fill the entire pop bottle with water and put it in the freezer, and then after 1 or 2 days you will see that it's bulging, which means it is changing the volume. The pressure did not make much of a difference, but the temperature did, right? So always in compressed liquid region, we look for the temperature. So once we figure out that this is in compressed liquid region, then we have to shift our gears and start our search using temperature entry tables because it's easier that way, right? So we don't care about the pressure anymore. Now we stick to the temperature. And then we said that the specific volume of a compressed liquid at any pressure is similar to that at VF of that given temperature, that of VF at that given temperature, right? So now this is going to be our VF at 10 Celsius, right? So now we locate our VF at 10 Celsius and then we can straight away pull that up for our VF. And we agreed that we don't have quality for compressed liquids or superheated vapor. So this is going to be non-applicable. And then this is compressed liquid. Or we can say that subcooled liquid, right? So these are kind of synonyms. So like you can use compressed liquid or subcooled liquid. So if in a question, if you see either compressed liquid or subcooled liquid, so it means the same thing. So now we discussed how to use property tables, like, and how to determine phases based on the information given. That's a very important component of this course, and it will help you to excel in all type of questions, not even the ones that we are discussing right now, like even the ones properties that we have not learned. This basic knowledge is very important. So now we are looking into another important aspect of this one, something you are kind of familiar at this point, the equation of state for ideal gas, right? So in your high school, you should have seen this equation in the form of PV equals mRT or PV equals N, not N, M, nRT. So out of these two forms, what is more familiar for you? Are you? nRT is more familiar, right? Yeah. So we'll discuss what's the difference between the two equations in the coming slide. So for now, for the purpose of discussion, we'll not be using the familiar equation for you, sorry about that, but we'll clarify the difference between MRT and NRT in the Jiffy. Okay, so bear with me until then. So let's assume, as I say so, like this is the correct equation as well, similar to the one you know already, right? So let's assume I'm not a liar, so PV should be equal to MRT. The mass of P is the pressure, and V is the volume, and M is the mass of the substance, R is the gas constant, and temperature is T is the temperature in Kelvin. Okay, so if we divide this whole equation by M, the both sides, then we can see that it becomes V over M equals RT, and essentially we can say that P into specific volume is equal to RT. So this is the one that you see up here, right? So pressure into specific volume is equal to gas constant into temperature. So I am pretty sure that you have used this equation in another form, NRT, the mole-based form, right? So even in that case, the most important thing or the most common mistake that we do is we forget to use Kelvin scale for temperature. So in this equation, you have to apply the temperature in kelvins and kelvins only. If you do not, if you do not apply the temperature in kelvins, your answers are completely wrong. You are going to lose a bunch of marks, right? So I'm sure that you have played with these equations already in the mole form, and you have applied the temperature in Kelvin form already. But you would be surprised how many students forget to do that in this course. So please keep that in mind. Temperature in Kelvin. If you see ideal gas equation, temperature in Kelvin, right? So let's move on to the next one. So before moving into using ideal gas equation, we should know when we can use ideal gas equation, right? So this is suitable for superheated gases at low pressure and high temperature. So you can see that low pressure, right? So as we go up in this direction, the pressure is increasing, right? So low pressures, okay? So this region falls under low pressure argument, okay? Or very high temperature. Very high temperature is here, right? So then, like this is the region that we can possibly apply this equation. And why do we have this constraint? Because in this equation, for a given pressure, right? You can look into one of these lines. For a given pressure, now these are given pressures, right? For a given pressure, this equation says that specific volume and temperature have a linear relationship because R is a constant, right? R does not vary. For a given substance, R is a constant. So for a given pressure, specific volume and temperature should have a linear relationship if this equation is true. So we can only observe linear relationships in this region, right? So otherwise it has a curvature, right? That's why, and definitely like for this region we cannot use it because it's not gas. It is liquid plus vapor, a mixture of everything, right? So that's why we can only use this relationship in the given region. And specifically, this is not suitable for states near the saturation region and critical point. Why is that? You can see the reason. So it is a curve, right? So when it is curving, then it's not suitable, right? At very low pressures, it can go a little closer to saturation vapor line, but in general, it's not suitable to use the ideal gas equation near the saturation line or critical point, right? Now, here's something interesting. You remember I emphasized don't use the ideal gas equation for water, right? And this slide does not change that statement by any means, right? So if you have property tables, you have to stick to property tables in the case of water or any substance because it's more accurate. It is developed based on empirical results or experimental results, right? So the ideal gas equation is an assumption or an approximation. And can we use ideal gas equation for water vapor or not? It's kind of a yes and a no, right? So in these regions, you can see the lines are curved, right? And these regions, they don't recommend us to use it as well. But like after reaching a certain temperature number, and even if the temperature is not very high, but the pressure is very low, then the blue colored region, they say that water vapor can also behave as an ideal gas. But do we use ideal gas assumptions for water in this course? No. So for water, do we apply ideal gas in this course? No. So if you apply ideal gas equations for water, would you get marks? No. Are we clear on that one? Perfect. And now here comes the most weighted slide. So to clarify the doubts we have about the moles and mass, right? What is MRT and what is NRT, right? So in the equation, you know, we had the moles, right? N is the moles. And R we use there is the universal gas constant. So universal gas constant in the sense, as the name implies, it's universal. It does not change from one gas to the other, right? But in the equation that we use now, the gas constant R is not universal. It's subjective to each gas. So it changes with the substance. For oxygen, we have a different gas constant. For nitrogen, we have a different gas constant. Why is that? Because we derive this R value by dividing the universal gas constant by molar mass. Dividing the universal gas constant by molar mass, we calculate the universal gas constant. Therefore, this is dependent on the substance, right? So essentially, what we did earlier in this equation is PV equals M divided by M RT. So previously, we divided the mass of the substance by the molar mass, and therefore we got the number of moles in that particular instance. In this course, we use this form of the equation. Essentially, both do the same thing, but the gas constant, instead of dividing the mass, this time we divide the universal gas constant by the molar mass. Are we clear? Any doubts? Anything not clear here? Perfect. Now let's see what procedures should we follow in finding properties of a pure substance, right? The first thing, always go to solution, is use the thermodynamic tables if they are available. So it is specific to a given substance and they are more accurate because they are experimentally tested and validated, right? And then the second one, if we don't have the property tables, and even if we don't have the property tables, we cannot use the ideal gas equation unless these one or both of these conditions are met, right? if our temperature is significantly higher than critical temperature, then we can possibly justify the usage of ideal gas equation for such a vapor or such a gas, right? And if our pressure is really low compared to critical temperature and our substance is away from saturated vapor line, then we can use this assumption, right? So even though we don't allow using ideal gas equation for water vapor, we allow using ideal gas equation for air, right? So in this course, you can use ideal gas equation for air. And when we don't have the ideal gas behavior, and still we don't have the tables as well, then we have another model including a compressibility factor to account for the deviations from the ideal behavior. So the third model we have not discussed yet. This one we have not discussed yet. It is an approximate model, and it is reasonably accurate over a range of substances, right? So we'll discuss why and how and when we can use the third one, in the coming lecture. But for now, let's focus on the other two aspects. Okay, now there's an example question which I will solve myself with you. Is it reasonable to assume that the following substances shows ideal gas behavior in following states, right? So just by looking at a substance, we cannot just say whether it will behave as an ideal gas or not, right? Because even something like nitrogen could be liquefied, right? So if we liquefy the nitrogen, can we apply the ideal gas law? Because we cannot, because it's not even a gas at that point, right? So it all depends on the condition. So let's look into the solution. So what we try to do here is we try to check our temperature against the critical temperature. You remember, if our temperature is significantly above critical temperature, then it behaves as a gas irrespective of the pressure, right? If our temperature is significantly higher, then we can say that it is suitable to use ideal gas equations under these conditions. So now we can find the critical temperature for different substances using table A2, right? So we locate critical temperature for oxygen, and it is 155 Kelvin. So 30 Celsius means it's 303 kelvins roughly, right? And is it significantly higher than the critical temperature? Yes, right? Because it's almost 2 times the number. Therefore, definitely it is significantly higher. So we can assume ideal gas behavior. And then methane. For methane, the critical temperature can be found to be 190 K from the same table. And there, again, our temperature, the state of the substance that we are talking about, is at 30 Celsius, which is 303 kelvins or 303 kelvins. This is again significantly higher compared to the critical temperature, right? So then in this case, we can assume ideal gas behavior. Are we clear about the first two, A and B? Are you doing good? Perfect. And for C and D, we have water and R410A, right? To determine the state of water and R410, we can use the property tables, saturated property tables, and by that you can determine the phase. Water and R410A at 30 Celsius and 3 megapascals are compressed liquid. So you know how to determine the phase of a substance. We did that in the previous examples, and use the same process and if you have a compressed liquid, it's a joke to use ideal gas equation, right? So it's a liquid, and we try to apply an equation which was developed for gas, right? So we cannot do that. Therefore, these cannot be represented with ideal gas equation, right? And then again, R410A, when we have a very low pressure compared to saturation pressure, that is somewhat similar to what we had here, right? When we have low pressures compared to saturation pressure, right? So in this case, we can use ideal gas equation. So how to know which table to use, right? The first thing you'd have to see if it is a gas. If it is a gas, then we check, okay, we know this is a gas, and we check the critical temperature. So if you don't know what is like A2, like even personally I don't know what is A2. So like if I want to know the critical conditions of a given substance, then what I do is I go to this table and I press Control F and I say critical. I search for critical, and then it pops up the critical constants, right? So there you find the critical temperature, critical pressure, volume, and stuff. So likewise, if you want to know, like let's say, that's how you deal with the gases. For other substances, first of all, you need to know whether these are in vapor region at least before coming into any conclusions, right? So if it is not in vapor region, like there's no point even checking the other parameters. Then, therefore, you use the saturated property tables to determine the phase of the substance. And even after determining the phase, like as in E, let's say in E, you figure out that it's a vapor, right? It's a vapor. Once you know that it's a vapor and you check the other conditions, the pressure, you remember I mentioned you either need to have a very high temperature compared to the critical temperature or very low pressure compared to critical low saturation pressure, right? So using that, we can determine the state, like whether we can use the ideal gas equation or not. Okay, so this question again, I will solve with you. So following gases are planned to be filled into a chamber. There's a typo, I believe, at room temperature into separate 1 cubic meter tanks at 20 Celsius temperature and 200 kilopascals pressure, right? How much mass is in each container is filled with following gases, right? So when we see this question, we feel the urge to use the ideal gas equation, right? So, but before using the ideal gas equation, we need to check whether we can use the ideal gas assumptions for this condition, right? So for air, like if you check the critical constants table, like for air, we don't have a substance as air in there. So what we can do is we can check the constituents of air with whether like the critical conditions of the constituents of air, nitrogen, CO2, and these substances, right? So we get the critical temperature for nitrogen and critical temperature for CO2 as well. So it's very low, it's very high compared to the conditions that we are talking about, right? So therefore, like our conditions are very high compared to the critical conditions. And at the same time, for all the constituents like that we have here, the pressures are very low. The critical pressures are very low compared to this one, right? Very low compared to the pressures that we have. Sorry, I'm trying to say it the other way, but it goes again and again. The pressure we have is very low compared to the critical pressures we have of the substances. So for all the substances we have here, we can use the ideal gas assumptions. That's what we have done here, right? For air, we didn't have an exact air column or exact detail about air. That's why we had to go for nitrogen and CO2, nitrogen and O2, right? So then for argon, we have the substance. So we check the critical conditions of that substance against the conditions that we have. Propane, the same deal. After verifying that, we can use the ideal gas equation. Then we can substitute the values. Pressure, volume is given as 1 cubic meter, and gas constant of air is 0.287, right? So to find these gas constants, again, I will go to my property tables and try to find ideal gases, ideal, and so there we have the gas constants, right, for different substances, table A5. So you don't have to memorize the table numbers, but you can just find. As this is in online environment, it's even easier. You can just press Control F and go from there, right? Okay, yeah, maybe the solution have one difference, like we have used neon in this one and the solution is given for argon. So in this case, please change the name of this one into argon. That is easier at this point. In this course, unless you are asked to check for ideal gas behavior, if you are asked to check for ideal gas behavior, if you ask whether we can use ideal gas assumptions for a given context, then you are supposed to check that. But I will not leave that ambiguity for you. If I expect you to use ideal gas assumptions, I will give you that hint. Use ideal gas assumptions in this solving this question. So there you get the hint. Okay, we can go and use ideal gas equation.